Ladies and gentlemen, welcome to this lecture on future trends in electric car technology. In this lecture, we'll briefly look at the important technologies and emerging trends in electric vehicles and charging infrastructure design. We will look at the powertrain design, solar electric vehicles, and fuel cell electric vehicles, future charging technologies, and finally at autonomous electric vehicles. First, let us look at the key trends in electric vehicle powertrain and battery technology. Amongst electric vehicle manufacturers, it has been now unofficially recognized that electric vehicles in the future must have a battery capacity that can provide at least 200-300 mile range. This is more than sufficient for city commutes and removes the range anxiety on the highway for long-distance driving in combination with the highway fast charging. Secondly, manufacturers are moving towards designing electric vehicles from the bottom up rather than building them based on existing combustion engine cars. This approach provides more flexibility in design, scope to add larger batteries, and is expected to reduce the cost of the vehicle in the long run. A third trend is to integrate the different powertrain components and controllers in the vehicle. This allows an increase in the power density with a subsequent reduction in vehicle weight, reduces the wiring requirements within the car, and provides more efficient ways for thermal management of powertrain components. The use of wide bandgap semiconductor devices such as silicon carbide and gallium nitride would help increase the switching frequency of power converters and hence increase power density. On the battery side, the battery pack voltage is increasing from 400 volt to 800 volt, providing increasing charging power for the same charging current. A vital parameter to realize more efficient electric vehicles in the future is energy density. The table shows the estimated maximum energy density limits of different battery chemistries. It can be seen that there is a theoretically up to 5-fold potential to go from the current lithium-ion energy density of 200 watt-hours per kilogram to up to 1000 watt-hours per kilogram possible with lithium-air batteries. There is hence a huge potential for research into the materials, stability, safety, cycle life, power energy density, and manufacturability of these emerging battery technologies. Besides this, supercapacitors can provide high power densities when used in collaboration with the battery for peak powers requirements during acceleration and braking. The second technology for future electric vehicles are solar electric vehicles. In the picture, you can see the solar-powered electric vehicles Nuna and Stella, designed by student teams at the Delft University of Technology and Eindhoven University of Technology from Netherlands. While the Nuna is designed to be a race car, the Stella is a family car. The common feature in both vehicles is that solar panels are used for charging their onboard battery and provide practically all the energy needed for driving. For example, in the Nuna 8 solar race car, 391 monocrystalline silicon solar cells with an efficiency of 22.5% were used. Other photovoltaic technologies can be used as well, depending on the flexibility of the cells, efficiency, color of the cells, and of course, the cost. In this figure, we can see the typical drivetrain components of a conventional electric car showing the battery, DC-DC converter, and DC-AC motor drive. In case of solar electric vehicle, solar panels are included in the drivetrain through a maximum power point tracking or MPPT DC to DC power converter. This converter ensures that solar array is operated at its optimal point and the voltage of the photovoltaic array is matched with that of the high voltage bus inside the electric vehicle. While providing all the power requirements of a commercial electric car using onboard solar cells would be not possible in the near future, several electric vehicle manufacturers have announced to have solar cells integrated into the car roof. This will partially provide the driving energy, thereby extending the car range. While solar cells can help in increasing the range of the electric vehicle, fuel cells powered by hydrogen can provide long driving range and quick fueling times similar to combustion engine vehicles. A fuel cell electric vehicle is essentially an electric vehicle with a battery, with the key feature of using a fuel cell to charge the battery and power the drivetrain. Production versions of fuel cell vehicles have been offered by several leading car manufacturers, including Toyota, Honda, Hyundai, and Mercedes. While high cost of the vehicle and charging infrastructure have limited its growth till now, fuel cell electric vehicles are expected to emerge back in the future and play a key role, especially for long-distance heavy vehicle transport such as trucks. Next, let us look at the vital technologies for future electric vehicle charging, namely battery swap technology, wireless charging, smart charging, and vehicle-to-grid. Battery swap works on the basis of switching out the depleted battery of an electric vehicle and replacing the same with a full battery. Battery swap has plenty of advantages, amongst which the most important are the fast times to replenish and empty the battery, and the flexibility to charge the battery at the swap station over a longer time when compared to fast charging. However, the main challenge for battery swap comes from the vehicle design. Large-scale adoption of battery swap technology requires electric vehicles to be designed with a standardized battery interface, and vehicle chassis that allows easy removal, charging, and placement of the batteries back to the vehicle. If the traveling routes, load factor, and vehicle fleets can be known, which is quite often the case for the public transport or commercial logistics, battery swap can provide a low-cost, flexible, and convenient method for electric vehicle charging in the future. Speaking of convenient charging, wireless inductive charging of electric vehicles would provide easy and convenience of charging without the requirements of any charging cables. The technology uses two electromagnetically linked coils that exchange power at high frequency. The primary coil is placed on the road surface and linked to the electricity network, while the secondary coil is placed on the vehicle and charges the battery. Wireless charging systems are now commercially available for various electric vehicles. In the future, it could come as a default charging system for electric cars based on the SAE J2954 standard. The extension of wireless charging would be on-road charging, where inductive charge pads are placed along the roads so that electric cars can wirelessly charge while driving. It's a technology that can dramatically reduce the cost of electric cars, as they would need a smaller battery and move this cost to the charging infrastructure. An excellent example is the online electric vehicle system developed by the Korean Advanced Institute of Science and Technology, KAIST, where 100 kilowatt wireless charging power is provided to buses at an air gap of up to 17 centimeters at 75 to 85% efficiency. This has resulted in the battery size reducing to 20% of its original size. There are some other future developments to mention, where different technologies are integrated. Solar and wind energy next to the road can, for example, power the electric vehicles by on-road charging. The roads can be self-healing without potholes and cracks. The coils used for inductive charging could make the same road with a special asphalt also self-healing. The roads can generate energy, for example with solar roads technology, where solar cells are integrated in the road itself. The third key charging technology is smart charging, especially from renewable energy sources like wind and solar and vehicle-to-grid technology. Smart charging of electric vehicles, whether it is AC, DC, or wireless, involves the control of the charging power as a function of time. By controlling the charging power, several benefits can be achieved in the future as enlisted, namely reducing the charging cost, charging based on renewable energy generation, using the car as a storage for the renewables, and a grid backup with the use of the vehicle-to-grid, and providing demand-side management and reducing the peak load and losses in the distribution network, as well as providing ancillary services in the form of voltage and frequency control to the grid. Lastly, the technology can totally change the mobility landscape is autonomous driving. Self-driving with limited capabilities have already been built into existing electric cars, such as those from Tesla. Self-driving vehicles open up a plethora of opportunities in the future, such as shared and connected mobility, cities decongested of cars and parking spaces, higher utilization of vehicles, lower cost of mobility, and more efficient point-to-point connectivity. A combination of different kinds of sensors, such as video camera, light detection, and ranging of radar sensors, ultrasonic sensors, and GPS, are used by the vehicle to understand the environment, and a computer on board controls the movement of the car. Autonomous driving is expected to be developed over 5 levels, starting at level 1, where the car can control either the steering or speed under certain conditions, to level 5, where the car can control and autonomously drive itself under all conditions. To wrap up this lecture, we looked at the key emerging technologies for future electric vehicle, focusing on the vehicle powertrain and battery and solar and fuel cell electric vehicles, battery swap technology, wireless charging, smart charging, vehicle to grid will be 4 key technologies for charging of cars in the future. Finally, self-driving cars can change mobility as we know it and change the landscape to shared and connected cars in the future.